Good morning, everyone. Welcome and thank you for joining us for today's chromatography webinar. Today's webinar is focused on the basics of Prep HPLC. The webinar is being led by Jack Silver, Teledyne ISCO's application specialist. If you have any questions during, please utilize the chat function within the Zoom platform. At this time, I will turn it over to Jack.
Good morning, everyone, and thank you very much for your time. I see that we have some people from Europe, and so good afternoon to you, and also thank you for your time. This is going to cover some fundamentals, and we're going to discuss liquid chromatography. We're going to talk about the types of chromatography, an overview of HPLC, types of runs, how to develop a method, loading capacity and column loading, and those are sort of intertwined, how to take care of your column, and we're going to discuss troubleshooting and why our peaks, why do they have poor shape. So what is chromatography? Well, for our purposes, chromatography is the separation of compounds in a mixture. Because we're talking about preparative LC, I'm not going to spend any time on analytical HPLC, except how can I use analytical HPLC to help me develop a preparative method. Chromatography that we are all familiar with include thin layer chromatography, flash chromatography, HPLC, which is divided in analytical and preparative. UHPLC and HPLC is essentially HPLC using smaller particles and higher pressure. Ion exchange, size exclusion, counter-current chromatography are outside of the scope of this presentation. So we're going to compare different types of liquid chromatography. Smaller. The flow rate range also gets smaller. The back pressure increases and the capacity, that is how much sample can be purified, decreases. UHPLC, while there's obviously a capacity, it's pretty much useless for preparative work because the capacity is nanograms to micrograms of sample. Thin layer chromatography is something we're familiar with. It's a quick method to determine reaction status and impurities, and it's a good method for flash chromatography. You can use C18 TLC plates, but it takes a very long time. Flash chromatography is a rapid purification method using inexpensive columns. It's usually silica gel, but other phases such as C18 can be used as well. Flash chromatography and prep are really very similar to one another, and in fact, I will use flash chromatography examples for illustration of preparative chromatography concepts. Sometimes the same instrument can be used for flash and prep. The image on the right is an easy prep system with a preparative LC on one side on the left, and it takes a flash column over on the right. Preparative HPLC uses small particle sizes. It uses high pressure. You get higher resolution. It's usually C18, but other phases can be used as well. The image over here is the AccuPrep system, which is for preparative HPLC only. We're going to spend a little bit of time on some definitions and theories. The stationary phase is the column packing, and it is not supposed to move. The mobile phase is the solvent that's pumped through the column. It is the we have a strong solvent which is added to the mobile phase that causes the compound to move down the column faster. You will also hear it termed the B solvent. The weak solvent controls the strength of the strong solvent or the A solvent. For reverse phase, water is usually the weak solvent, with methanol or acetonitrile being the strong solvent. For the theory of retention over here, we have a compound that is partitioned between the stationary phase and mobile phase. These little circles are intended to represent the column packing, and obviously the molecule depicted here is a lot larger than it would exist in real life. Equilibrium to the right is less retention, and it's early elution, as you can see with the yellow compound over here. It spends more time in the mobile phase, so it runs down faster. Equilibrium to the left, as with the blue compound, is a late elution. The equilibrium is to the right. It spends more time stuck on the stationary phase, so it doesn't move as much. Types of column packing, you have normal phase, which is the original type of chromatography. That's why we call it normal phase, is once upon a time it was what was normally run. Packings include silica, alumina. The column packing is polar compared to the solvent. The solvent is an organic solvent that is nonpolar. Hexane, cyclohexane is very commonly used. Dichloromethane and methanol are used. For a normal phase, stronger solvents are more polar, and you can get silica columns or alumina columns as preparative HPLC columns. If you're working with chromatography, at least some of those are really normal phase columns, and so the more polar solvent causes the compound to elute faster. Types of column packing again include reverse phase, and that only became practical around 1970, or quite some time after normal phase became common. You use C18, C8, C4 phenyl. There's a column made out of polymer. It's a polymeric reverse phase. The column packing is nonpolar. The solvent is polar compared to the stationary phase. It usually contains water. In this case, stronger solvents are less polar, so you see it's the opposite of normal phase. That's why we call it reverse phase. So why do we use HPLC? I said earlier that flash chromatography worked very well. All of the concepts that apply to flash, I'm going to use for HPLC, so why would you use it? The equipment costs a bit more. Flash uses very cheap column, whereas a Prep LC system uses expensive steel columns. Well, one word, resolution. We have smaller particle sizes. The packing is improved, and there's a lot more control over the packing. More attention is given to extra column volume, that is the tubing and fittings, to reduce band broadening. That gives us the ability to resolve closely eluting compounds. So on top is a mixture of capsaicins, a natural product. It was run on a flash HPLC, on a flash chromatography system. And you can see that I could resolve 3 peaks very reasonably well, but they don't have baseline resolution. The same mixture run on an easy prep, I can get nearly baseline resolution, and I can see additional compounds. So I have a shoulder over here on the first eluting peak. In between peaks 2 and 3, there's another little peak hiding, and I actually get baseline resolution on the last peak in the group over here. So we get much higher resolution at the cost of sample loading, as we saw in an earlier slide. So how do we affect resolution? Well, there's 3 major parts to the resolution equation. You have efficiency, retention, and selectivity. We can increase efficiency by reducing the particle size, and we've done that by using particles so small that we have higher back pressure. You can change retention by changing the solvent strength, and you can change selectivity by changing either the column or the solvent system. So what is this magic selectivity? Selectivity is really the relative elution of two different compounds. By changing the selectivity, you can make one peak elute earlier, faster than another peak, or you might even be able to reverse the retention so that the peaks come out in the opposite order. So by changing the solvent strength, the percent B or the B solvent, I can also adjust the resolution. I have here a series of isocratic runs, and the first example shows 45% methanol. I can make the peak elute a bit earlier, about 75% earlier, or 0.75 earlier, by going to 50% methanol. I can reduce the retention time by another 75% by going to 55% methanol. And I trust that you could see a pattern here. For these isocratic runs, if I increase the percent B by about 5%, the retention time is changed by about 75% as a rough approximation. So 8 times 0.75 gives us the 6 minutes, and then another 0.75 gives me the 4.5 minutes. So it's a pretty rough guide, but it helps you when you develop methods later that you can set up a method, and if you want the peak to elute earlier and later, it's a fairly rough guide to how to adjust the solvent. So if you want the peak to elute later, you make the solvent weaker. If you want the compound to elute earlier, you increase the B solvent. The other thing that we can adjust is selectivity. Solvents in the same selectivity group differ mainly in strength. So in group 6, where you see acetyl nitrile, you also see acetone as well. And you can use acetone as a HPLC reverse phase solvent. It acts very similarly to acetone, except that it's what we would call a stronger solvent. The numbers in parentheses are less polar. Water does play a role. It's part of a selectivity group, and so for that reason, you have less choice in changing selectivity by changing solvent as you do in normal phase chromatography. You can do it using modifiers with ionic compounds, and I hope to show that later. The last term is efficiency. It's measured by theoretical plates. Efficiency is determined by the length of the column divided by the particle size. It's in proportion. So a longer length causes higher back pressure, more diffusion. Smaller particles cause higher back pressure. So getting more efficiency comes at a price of back pressure. Over here is our compound, and it's run isocratically. The compound runs at about 6 minutes at 50% solvent on a 20 by 150 column. Running the same solvent system on a 250 millimeter column, the compound elutes at about 10 minutes, and that makes sense. 6 minutes times 250 divided by 150 equals 10 minutes, and that holds up pretty well. I'm also going to ask you to kind of remember this compound for future use. 50% B, it comes out at 6 minutes. I'll show you why that's important when we come back to method development later. Types of gradients you can run is isocratic. It's one constant solvent composition. It's the most easily run because you just set the solvent composition. It provides the highest resolution with a potentially longer run time depending on the resolution that you need. You might not be able to purify all of the compounds in a mixture in a reasonable time because some of them come out very late. In this example over here, I have a compound eluting at 6 minutes. I have something else coming out later, and in fact, I have a step gradient to 100% B to wash out the column and clean it. And that's usually a good idea to do after running a column. If you're running a shared system, it keeps the column clean for the next person. It also eliminates ghost peaks that I will discuss later. Step gradients, I just showed you an example of one. It's used in flash production. It's a series of isocratic steps. The one I just showed you was 50% B, followed by a step to 100% B. Linear gradients are broken down into two groups. One of them is what I call scouting gradients, and the other one are focused gradients that use a limited range of solvent compositions. It provides similar resolution as an isocratic, and it allows for some error in setting the optimal solvent composition. A linear gradient shown over here is useful if all compounds need to be purified. If we were interested in this compound or this compound and this last compound that's eluting, you could not make an efficient isocratic gradient to collect these in anything other than maybe an hour or so, because these compounds elute in maybe about 20% solvent. This elutes in about 90% solvent. However, a linear gradient is useful if you need to purify all of the compounds, such as people working with natural products. If there's a wide difference in compound retention. The gradient I have here is an example of what I term a scouting gradient. So the scouting gradient starts at some low % B and goes up to some very high % B, typically 95 or 100% B. The other type of linear gradient is a focused gradient. The resolution is similar to an isocratic, but it's less sensitive to solvent composition and temperature. For example, you might remember earlier that just a 5% B change in solvent composition moved a peak several minutes. Over here, a 5% B change in solvent composition might have moved a peak only maybe 1 minute or so. Another thing that isocratic runs are somewhat sensitive to is temperature. Sometimes the peaks elute earlier or later as the temperature in a room changes, and that can affect the retention. So running a linear gradient, it reduces the effects of temperature. So what are the goals of method development? We want to purify the compound quickly. We want a fast run. Ideally, we want the compound to elute in something like about 6 minutes or so. If you need to run a longer column, maybe 10 minutes. We want high loading, which goes with having high resolution. We want to minimize solvent usage, and that goes with having a very fast purification. We want to minimize any workup, so we prefer volatile solvent modifiers. So how can we purify a particular compound with an optimal gradient? Well, flash chromatography uses TLC plates for method development. This compound elutes with a retention factor of 0.3, 10% B. So if I set a focus gradient from 5 to 15% B, the compound elutes in the middle of that gradient. Okay, C18, you can run a TLC plate. It will take a very long time. So what we will do is a scouting run. And the scouting run will then allow me to see when the compounds elute. The problem is, as you can see from the orange line, is that the gradient is delayed by a certain amount. So how can we work around this? One way is to define zones. So a compound that elutes in this zone, you set a focus gradient from 1 to 5% B. Zone 2, 3, 4, you have certain solvent compositions for a focus gradient. You have to empirically determine this with test standards and see which zones will work for you. For any sort of method development going from analytical to prep, you need to use the same column chemistry in the prep and the analytical. So Waters makes several types of columns, micro bonder pack and different types of columns. And in fact, so does Teledyne. We have C18RF and C18AQ. And if you use different columns, you're going to get slightly different selectivities, and that will throw this off a little bit. One disadvantage of these zones is that the gradient that is made from a zone is not necessarily optimal for any compound. So in zone 2 over here, you can have a nice gradient for this compound. The compound eluting at 3.6 will elute late on the gradient. Likewise, in zone 4, you can get a very nice optimal gradient for the compound eluting at 6.8. The compound eluting at about 6.3 minutes will elute early in the gradient. However, these zones are very easy to understand. Another way of calculating a gradient is to estimate the solvent composition that elutes the compound. Over here we have a mixture of compounds, and this compound over here at about 9.5 minutes is the compound that we were running earlier that elutes at 50% B and elutes at 6 minutes. So I have my scouting gradient over here. And what I do is I note the time that my model compound elutes at, and then I look at the time where I programmed the gradient to be 50% B, and I see the difference in time. I can then apply that same time difference to other compounds. This analytical scouting gradient with the model compound is run separate from your compound, and once you determine that delay time, you can just run all of your analytical compounds and apply the same delay time. So this peak number 1 over here, I apply the delay, it will come out at about 20% B. This last peak over here, which looks like it comes out at 100% B, really comes out at about 90% B. And stand by. Okay. Focus gradients from the scouting gradient are forming over here. In this example over here, the first peak does come out at about 20% B, and it comes out at 6 minutes. That happens to be the same time that I used for the model compound that I showed you on the Isocratic runs earlier. Likewise, peak number 4 that elutes very late now comes out at 90% B, just as the delay suggested. So this is a pretty good way of calculating a focus gradient. The method can be further fine-tuned, and next year we will have a webinar describing how to accurately calculate a gradient from a scouting gradient. There's a couple of other parameters that can be applied to make it very precise. However, the method I just described will get you very close indeed. Solvent modifiers are used to improve peak shape. I mentioned them earlier, and now we can talk about it. They modify the pH and the solvent polarity, and they reduce interactions with silanols on the column, and they shift the acid-base equilibrium on the compounds you are trying to purify. When choosing a modifier, remember that you will have to remove it. A volatile modifier is the easiest since it can be evaporated or freeze-dried. If non-volatile buffers are needed, you will need to apply a desalting step, and we do have an application note up on our website that describes using a C18 column for desalting. Modifiers also need to be compatible with the detector, whether it's a mass spectrometer or an ELSD. If you're using one of those detectors, you have to use a volatile buffer, otherwise you're going to, at a minimum, have reduced sensitivity. You might even clog up the detector. Modifiers also need to be compatible with the column. Since most silica-based columns are dissolve in basic conditions, you can't run them above pH 7.5 or 8. Otherwise, the silica dissolves and you wind up with a ruined column. So again, why modifiers? We have a carboxylic acid over here and a primary amine here. When we ionize them, they become much more polar. When running reverse phase, more polar compounds elute earlier. Neutral compounds, however, they are affected by solvent modifiers, but not in the way that you might think. Neutral compounds, they don't ionize. However, the solvent modifier makes the mobile phase more polar. It makes it act like a weaker solvent. That means then that neutral compounds will actually elute a little bit later when solvent modifiers are employed than when they are not used. Some of the effects of modifiers: acridine run in water and methanol elutes at about 5 minutes. My gradient goes from 5 to 100% B, and the gradient ends at 5 minutes. I also have a little impurity that is eluting. When I run the same mixture in water and methanol with 0.1% TFA, the acridine elutes a lot earlier. That's because it's a basic compound. It's eluting as a polar compound, and so it will elute a little bit earlier. You also note the distance between the acridine and this impurity is greatly reduced. I've also changed the selectivity somewhat, although not necessarily in a positive way for this example. However, for this run, we would still be able to purify the acridine from the impurity on a preparative system. Another example is nicotine run in water methanol. It elutes at about 3.8 minutes, and when run with TFA, it elutes nearly at the void. It shows a very great difference in retention. If you have basic compounds and neutral compounds mixed together, you can see how you can use modifiers to change the selectivity, because the polar compounds will shift the retention a lot more than the neutral compounds. We have salicylic acid that we talked about earlier, and salicylic acid elutes as a very broad band in water methanol, but by adding TFA, it makes a very nice sharp peak. The other thing to note is that it actually elutes later because I made the compound more neutral, which means it's less polar, which means it retains more on C18. Useful solvent modifiers include phosphate, ammonium acetate citrate. Some of the common modifiers, such as TFA, formic acid, or acetic acid, they adjust the pH, but they have low buffering capacity. LCMS compatible modifiers are also volatile, which means that they're easy to remove by evaporation or lyophilization. Buffering capacity is important because on prep HPLC, you're loading a lot of sample on the column. If you have a compound that is acidic or basic, it's possible that it can interact very much with whatever you're using to modify the pH. If you don't have enough buffering capacity, what could happen is that the compound, some of it is ionized, some of it is not ionized, and you can wind up with two different peaks of your compound, or you can wind up with very broad peaks. We'll mention this again in troubleshooting, but I'll mention it now since it kind of goes with this discussion. TFA tends to act as an ion pairing reagent, and it sometimes causes ion suppression in LCMS. Borate buffer is good if you're running basic pH, 8.3 to 10.3. However, silica dissolves above pH 7.5, and some silica stationary phases won't stand such a high pH. The other thing is taking care of your column is, at the end of the day, wash these modifiers out of the column. It helps your column last a lot longer. pK of several functional groups, carboxylic acids down pH 6.5 to about pH 5. Alcohols, and that includes phenols over here, have a pK of about 8.4. Amines have a pK in the ranging from slightly acid to basic. Imides have a basic pKa. So those are the ones that we are mostly concerned about. So solvent modifiers and PrepLC, how do they help us? I did a purification with nicotine, salicylic acid, and acridine, and I see 3 peaks, so everything looks okay, right? I injected 3 compounds. I got 3 peaks, so everything's okay, right? Well, let's take a look. We have a pure ion mass spectrometer that we can hook up to our AccuPrep or EasyPrep, and it allows us to look at the masses and collect compounds based on mass. What I see is I have a first peak that comes out. It has a mass of 163. I have another peak with a mass of 180. There happens to be nicotine and acridine. What's interesting is that I don't see the salicylic acid, and I have 2 peaks over here for nicotine. So something's a little funky over here. So I then run the same mixture in water methanol, except I added 0.1% TFA. As we expect to see in the analytical run, the nicotine comes out very early, and we can see it's matched very nicely. The acridine comes out later, and it comes out as a single peak. It eluted earlier than on the previous slide. Again, the same as what you saw on the analytical. And the salicylic acid now shows up very nicely because I was running ESI in positive mode. The salicylic acid doesn't show a mass spectrum, but I can still see it over there. So solvent modifiers really help you avoid some potential problems with your PrepLC. Injection solvents, what you dissolve your sample in is very important, and how you load the sample affects the resolution. It's very important to filter or centrifuge your sample. The frits on the top of the column are very fine, and if you don't filter or centrifuge your sample, particles can clog the frit, and they're very difficult to clean. They're very nearly impossible to replace without damaging the column packing, and those are very expensive columns. The other reason for filtering your sample is your inject valve. Those tiny little particles cause the rotor seal to wear more quickly, and it causes leaks. So using a manual injection technique, a fast injection limits the useful injection loop volume to only half the loop size. So if you have a 5 mil loop, you only can use about 2.5 mils of that sample loop, because what happens is the center runs a lot more quickly than the walls during injection, especially with viscous solvents such as DMSO or DMF. Using the auto injector or the auto sampler allow a much higher loop utilization. You can then inject 80 or 90% of your loop and make better use of the sample loop on the system. Dissolving the sample, you want to use the weakest solvent that is possible. A large volume of weak solvent is better than a small volume of strong solvent. DMF and DMSO help you to dissolve the sample, but it can cause issues with very polar compounds, as I'll show you shortly. The problem with injecting your sample in strong solvent, and some people will use, say, acetonitrile or methanol, is that you inject the sample and the compound, because it's in the strong solvent, doesn't interact very much with the stationary phase. And so your stationary phase gets pulled down the column instead of a nice tight band, as I will show you on a flash column. So on the left is a flash reverse phase column with the sample dissolved in the B solvent. And what we see is that we have a decent looking peak. We have some tiny little peaks at the front at about 1 column volume. And 1 column volume after injection, you can see that the colored compound is dragged down the column. In the right chromatogram, I dissolved the sample in water. After 1 column volume elution, the column still looks very nice. The sample is still underneath the cap over here. Somewhat later in the run, I get a nice tight band that's reflected in the chromatography where I have nothing eluting very early and I have much better peak shape. The dissolution, this happens on your Prep-LC system as well. I have a polar compound, resorcinol and catechol, dissolved in DMSO. This was a 1 ml injection, and it looks very nice and it's quite usable. We have another injection at 2.5 mils, and we could see that now I lost the resolution. I could still see my peaks, but now I don't have baseline resolution anymore. And some of the peaks are eluting with the DMSO. So this is the chromatogram from the previous page, and I dissolved resorcinol and catechol at the same concentration and ran it in 2.5 mils of water, and now I have baseline resolution again. I can even increase the injection volume to 4 mils, same concentration, so I'm injecting 4 times the sample as I did on the first run. I still have baseline resolution, so my loading capacity was greatly increased when the sample was dissolved in water. DMSO is weaker than the B solvent used, but it's still a stronger solvent than water. So the other thing to note is I have peaks that look like shark fins. That's okay. It's typical of an overloaded column, but because I still have baseline resolution, I'm not too concerned about the peak shape because I'm not doing analytical chromatography. Why would you use DMSO? Well, it's very easy. DMSO dissolves practically everything, so you don't have to hunt and find out which solvent to inject your sample. Sometimes, and I've seen this with peptides, there's a mixture of the peptide, which is water soluble, and some of the reaction byproducts that are very nonpolar. And sometimes the best way to get them into solution is to use DMSO. So DMSO, DMF are sometimes necessary evils, but they do reduce our sample loading with very polar compounds. Column care, the first thing, the most important thing is read the instructions that come with the column. Ready set prep columns do come with instructions that talk about somewhat flow rates. The instructions will often mention the maximum pressure, what solvents can be used. This is really important for chiral columns. Some chiral columns can't be used with just any solvent, and the instructions make that very clear. Also pH limits. Again, silica, most silica columns dissolve when you get above pH 7.5 or 8. If you buy one of the CombiFlash instruments, the AccuPrep or the EasyPrep, we do allow you to set the maximum pressure for a particular column so you don't ruin the column by accident by setting a high flow rate or something. sometimes you have to look on the vendor's website to find the back pressure limits, or the flow rates and so on, but read the instructions first. The other important thing is to wash out any buffers and modifiers after use. TFA, acetic acid, formic acid, those will hydrolyze the bonded phase. It happens very slowly, but it does happen. If you're using inorganic salts, you want to wash it out so that you don't precipitate anything in the column. You usually store in your stronger solvent. This way the column is washed for whoever needs to use it next. Troubleshooting pour peak shape, column, pH, the injection, ghost peaks. Some of these items, column, pH, and injection, we've talked about before. Loading, it's actually not an issue if the resolution is maintained. You might remember I had shark fin peaks, but because the peaks were well resolved, I didn't care about that. Column issues, voids. Voids can happen a couple of different ways. You can damage a column. Some columns, if you drop them, you can cause a void. Most modern columns are a lot more resistant to accidental drops than they were earlier, but that's still a possibility. If you run a column too fast and overpressure it, sometimes you can create a void. If you run a silica-based column above pH 7.5 or 8, if you can sometimes dissolve the silica and create a void. And over here, this, believe it or not, is just one compound, but the column was damaged so badly that I'm seeing it looks almost like 3 peaks in there. Another column issue is loss of bonded phase. You can have hydrolysis of the silo ethers, that these oxygen bonds over here at low pH. Again, it happens very slowly. But if you wash your column out after you're done using it, you can make your column last a lot longer. Also, dissolving the silica, you dissolve the silica underneath these silo ethers, and that means that there's nothing holding this in place. And again, it can wash down the column. So again, one more time, wash your columns before putting them away. The last thing I'd like to talk about are ghost peaks. There's several sources of ghost peaks. The solvents, they might accumulate on the column until a stronger solvent is run. And if that's the case, you see it during your first injection and not the later injections. If you want to look for ghost peaks, just run a blank column, and any peaks that come up are ghost peaks because you didn't inject the sample. I suppose another possibility is carryover from your injection system, but we're just keeping it simple here. Another thing you can do is increase the equilibration time and see if the ghost peak becomes larger. And again, you're just injecting a blank, no sample. So increasing the equilibration time and your ghost peak gets larger, it's your solvent. And the problem with ghost peaks is they're somewhat intermittent. Sometimes you see them, sometimes not. Your solvents might have impurities in them. The other thing is they might have other compounds, like for instance, tetrahydrofuran, THF. Sometimes you have a preservative in there that sometimes holds up on the C18 and elutes in the column. If you know it's in there, you know when it comes out, you can usually work around it. Also, I mentioned earlier in the presentation, previous injections, compounds with very long retention, just wash the column and then that helps to reduce that problem. So in any case, that's the end of my presentation over here, and I'm happy to take questions now.
Okay, and just a reminder to use either the chat function or the Q&A function to submit questions for Jack to answer. We do have one question that has come in, Jack. Is it recommended to inject the sample in mobile phase?
that would be ideal if you can inject the sample at using the same mobile phase as what elutes it. If you can inject this sample in a weaker solvent, that might be a little bit better since it tends to focus the sample at the head of the column. As was shown in this slide over here. In this case, I was able to inject the sample in water and it focused the sample very nicely, but mobile phase is a very good choice.
Okay. Another question that we've had come in. Could you comment on reuse of flash columns? I've had good results suctioning off remaining solvent prior to reuse.
I'm going to assume that the question refers to C18 reverse phase flash columns and other bonded phase flash columns. And those are designed to be reused many times. Although I don't suction off the solvent, I just wash them in methanol, and then I just put the end caps back on and I store them in methanol. Okay.
Okay.
Yes. Okay, and the question comes up with actually silica. The thing with silica is you can sort of reuse them. The problem is that you also absorb the mobile phase on it, and so you've changed the chemistry. So it can be very difficult to match your TLC results with a used silica column. Because you've changed the surface chemistry because the solvent's absorbed on the column. The other thing is silica tends to bind very polar compounds very tightly, so you can, your column actually acts as if it were a shorter column. Instead of just suctioning off the solvent, I like to flush it full of 2-propanol to keep the column preserved better. And also, the hexane ethyl acetate commonly used tends to swallow up the plastic, so flushing that material out helps maintain the packing. Another question that I have is, what standards would I use to test a semi-prep system? Nicotine or salicylic acid? Well, for our columns, we have a test mix. We actually have a couple of test mixes that we provide. The compounds that I used in my presentation where I showed the isocratic runs were phenacetin and N-benzobenzimide. And those also make a good marker for adjusting the retention time for a compound so I can calibrate an analytical system to it. Some other good reference compounds that I can run are the various, oh man, I'm having a brain freeze right now and I apologize. Send us your email and I'll send you a reply when I get the memory. Parabens, I'm sorry. Some of the parabens make very good test compounds because they also allow you to look at the state of the silica. And I like to run those isocratic because running isocratic tends to show problems with the column better than running a gradient. Okay, what is the technical difference between analytical and preparative HPLC and how to develop an analytical to prep method development? The technical difference is analytical is really intended to look at analysis. Is the compound pure? How pure is it? But it tends to run very quickly. And so what I can do is, as I showed a few slides ago, is I can either divide my scouting gradient into a number of different zones and then assign a focus gradient to each of the zones, or I can measure the delay of the model compound and then run a scouting run on that, and then I could apply the same delay to the samples in my analytical run. Okay, I have another couple of questions. Is there any bad effect of DMSO use on the column? The answer is no, certainly not for injection solvents. I've had the occasional person ask me to run DMSO as a mobile phase, and that doesn't work very well because DMSO has a very high viscosity and it will only run at a very low flow rate. It's not useful as a mobile phase. It is useful to dissolve samples and it doesn't hurt the columns. The other question is the best way to wash the solvent modifiers. The best way is just to wash with your mobile phase but without the modifiers. What I will often do is combine the two wash steps, that is wash any sample off the column and wash out the modifiers by just flushing my column with either acetonitrile or methanol, and then I'll put the column away with those solvents in it. Okay, another question is, I observed two peaks once for the same compound, but the same compound is elute as one sharp peak on the same set of conditions without any change. Could I explain this? Actually, I had the same thing happen to me. I was running the compound on the analytical system, and then when I took it over to the prep system, it showed up as two separate peaks. What I found the difference was my analytical system, I had the water from one source. I used bottled water, HPLC grade water, and for my prep system, I was using 18.2 megohm water from my water purifier. What happened is that I had a change in pH, and that's caused my peaks to show up as two separate peaks. If you're running it on the same system, you might want to check your water, check your pH. If you're running a compound that has a polar functional group that is ionizable, that is a carboxylic acid or an amine, I find it best just to use a solvent modifier just to avoid that problem altogether. Okay, another question. Is it possible to run this HPLC with solvents such as ethyl acetate and hexane since the compound comes in normal flash, 50%? I do not want to use high boiling solvents. In order to run the HPLC with ethyl acetate and hexane for a compound that elutes in 50%, you can buy a silica prep column, and you can run hexane ethyl acetate on silica prep. There's also a technique called non-aqueous reverse phase that is useful for very non-polar solvents, but such compounds won't dilute in 50% ethyl acetate and hexane.
Okay, and this will be the final question here coming in right now.
Okay. I have a compound that is charged but very hydrophobic. It's best run on C8 column with water and acetonitrile as a solvent. What should we do when we run this on C18? I'm reading that it's very hydrophobic, and if you run it on C18, there's about three things I would try. One of which is you might increase the concentration of acetonitrile. That makes it a stronger solvent. And so it washes a hydrophobic compound down the column more quickly. Another possibility is instead of using acetonitrile, use acetone or THF, which are both somewhat stronger solvents than acetonitrile on C18. And the third thing that I might try is using the non-aqueous reverse phase. We have a couple of examples up on our website. Yes, they are flash chromatography, but remember they're very similar, where I used non-aqueous reverse phase to purify very hydrophobic compounds off of C18. The fact that it's charged still suggests that you just might need a modifier even so, and if you need a solvent modifier, you still might be working with some degree of water. Can we give this presentation as material in an attached file?
Yes, so this presentation has been recorded, and later on this week or early next week, you guys will receive an email with a link to the YouTube recording. If you're looking for the PDF files of the webinar, please send us an email at iscoinfo@teledyne.com, and we can get that sent on to you.
Okay, I've got one last question. I'm going to ask you to send me an email to this person. How in general do you use reverse phase compounds to dissolve the compound? That takes a couple of steps, and if you send us your email over here, I'll be happy to send you the application notes that apply to that.
Okay. So at this time, thank you so much, everybody, for joining us for today's webinar, and thank you to Jack for presenting on this topic. I did want to let you know, so you'll be receiving an email later on this week with a link to this recording. And I also wanted to let you know that our next webinar will be taking place on January 23rd. The focus of that webinar will be the purification of low UV absorbing compounds by Prep HPLC. So be on the lookout for registration information for that upcoming webinar. We look to be holding webinars every month in 2019, so we're going to have a lot of interesting topics coming up. Again, if you have any follow-up questions or comments, please utilize iscoinfo@teledyne.com, and we can get you answered at that time. Thank you so much, everybody, for joining us, and have a wonderful day.